Introduction to Statistical Learning, Chapter 4, Question 12, which is the last, I believe, of the conceptual questions. We have A through E parts, and they're all dealing with this first part here. So the idea is that we have some data, and we fit a logistic regression to that data, okay, given here. All right, where we're finding the probability that the outcome is orange given the data. Okay, and then we have a friend who is fitting a similar equation but using the softmax formulation. Okay, so finding the same probability, but their expression is given here, and you can look at those for yourself and look at the differences. Okay, so now we go through to parts A through E. Okay, so part A right here is what is the log odds of orange versus apple in our model? Okay, so remember that the log odds, so we're given a formula for P, for the probability of something, but odds is P over 1 minus P, and the log odds is the log of P over 1 minus P. Okay, now we could just answer this if we knew the definition of our log odds, or, well, I shouldn't say that, how we might fit a generalized linear model to log odds. And in that case, we would just know that the way that we do that is we set the log odds equal to our linear expression. Okay, but we could also figure that out, and so that's what I do here. So remember, we know already what P is. P is this guy right here. So everywhere there's a P in here, I'm just going to input that expression. Okay, so here it is right here. Okay, notice this that we have this 1 here. So if I just give this term and this term the same denominator, right? I get this. So now I can put all of this over one denominator. So I have 1 plus all of this minus this. Okay, which ultimately gives me, well, I add it and I subtract it, so now I just get 1. And so now I have a fraction divided by a fraction, which means I take a fraction multiplied by the reciprocal of the fraction, right? I get that here. The natural log didn't carry over. I should have formatted that differently, but there's a natural log of all of this. Okay, this numerator and this denominator cancel out, leaving just e, and I forgot a parentheses, an e to the x beta over 1, which is just e to the x beta. So I have the natural log of e to the x beta, and when I take, if I take the log of an exponent, then those are inverses, so I just get x beta. Okay, and now that's generic form. Our x beta here, that just represents our linear model, and again, our linear model is this right here. Okay, so now we're going to do the same thing for our friend. Okay, so again, we're finding the same quantity, but now they've defined P differently, right? They've defined P like this. Okay, so if we go about doing the exact same thing, everywhere where I see a P, I input that expression. Okay, and let me explain this expression. So in where are we at here? Well, with the softmax formulation, we have the sum of all of the linear components of all of the models. Okay, and so what I've done here, so the denominator contains both the numerator and then every other linear combination for every other category. Okay, and often that's just written as one expression, but here I'm just pulling out the part of the big expression that is in the numerator. Okay, so anyway, so we go through the same thing. And you know what? I feel like I didn't explain that very well. Let me pull something up. Okay, so this is the actual book. Okay, so this is the logistic regression formula. Okay, so this is what we already were looking at, but this is the softmax formulation. Okay, and so in the softmax formulation, what we have is we have the numerator, which is the same as we had for the logistic part. Okay. But then in the denominator, we have this part, but for every category. So here it's category K, and then in the denominator we have categories 1 through capital K. But one of those categories here is lowercase k, which is one that we have in the numerator. And so all I have done is to separated everything that is in our numerator and not in our numerator. And the beta coefficients for the things that are not in the numerator, I'm calling gamma. Okay, so this is just a nice generic expression. Okay, now we just go through the exact same steps, and ultimately what we get is that the log odds can be expressed like this right here. Once again, it kind of cut off, and I should have done a better job formatting it, but here you go. Okay, so the log odds ends up being x beta minus the natural log of the sum of the x e to the x gammas. Okay, now in our problem, we only have two classes, right? We only have orange and apple. So that means that this sum right here actually only contains one other term, right? One other class. So we can simplify all of this by saying x beta minus x gamma, or we can just go all the way to here, pull out the x. Okay, so again, this is a generic form of everything. Okay, in our particular example, our linear expression for the log odds becomes this. Okay, so we have the coefficient for the intercept for oranges minus the intercept for apples, and then we have the slope for oranges minus the slope of apples times x. And again, that result is actually given in the book. It's equation 4.14, but we've just kind of gone through and derived it. Okay, now part C is, so we say that we find estimates for our coefficients of beta naught to be 2 and beta 1 to be -1. So that means that our log odds equals this, 2 beta naught minus 1 times x. Okay, so minus x. Okay, and so now we're supposed to say something about what our friend would find in terms of their coefficients. Okay, well, our friend has more coefficients, and so it's not really we can't. So our friend has intercepts for oranges and apples and slopes for oranges and apples. Okay, but what we so we can't say what the intercept for, or we can't say what the value for each of these is. Okay, but okay, so notice that our linear expression here for the softmax formulation, it's just a linear model. Okay, and so we have one part that's not multiplied by x and one part that is multiplied by x, corresponding to beta naught and beta 1x in our expression. So we see that the difference in the intercepts is 2, right, which was our beta naught, and the difference in the slopes is -1, okay, which was our beta 1. Okay, now we just go the opposite way. Now we have our friends, our friend runs their softmax, and they get the following estimates for the coefficients, okay, which are highlighted here. And so now we want to figure out what our coefficients are, and maybe even what our log odds would be. Okay, well, once again, so this would be the expression for our friend, okay, and this simplifies to that, and this again represents our intercept and our slope. Okay, so our beta coefficients would be here, and then we could even put an expression for the log odds, which would be, well, basically it'd be the same. Okay. Okay. Now, finally, so if what this is asking is, let's say that we were to employ both of these models, both the model that we made and that our friend made. Should we expect the two models to agree in terms of predicting classes? In other words, the probability of y given x, or what fraction of the time should we expect them to agree? And I think that, I mean, somebody should tell me if I'm wrong, but I think they should always agree, right? These are both equivalent expressions of the log odds, okay? And so, so just because they're different expressions, they're still going, the algorithms that are going to try to solve either formulation, they're still going to be trying to fit the same values, okay? And so they're going to kind of, you know, move around their estimates of the coefficients such to arrive at the same well, to explain the same quantity or to estimate the same quantity, okay, which is the probability of y equals orange given x. So anyway, I think I will call that good here, and I will see you in the applied questions next.